We were talking at dinner the other day about how the American news media tends to deliver everything as a developing story or breaking news. It's kind of a little bite-sized, detail-free talk. I hope that's not what this is going to be, but I should mention that all of these results are hot off the press, and so I'm not going to show you a whole lot of quantitation, but there's definitely a lot of qualitative data. And if you want to see more, give me a month, and hopefully we should have some good stuff. Okay, so one thing that's just wonderful about this is one of those rare moments in math where we've got a method that is subtle and beautiful and manages to describe a broad range of behaviors, very complicated sort of implementation. But in terms of what's actually going on, the underlying code and so forth, it's actually something you can kind of grasp very viscerally. To the point that I think that most everybody in this room is doing some flavor of this algorithm on a daily basis. And so that's what we're talking about here, is general purpose constraint optimization. We'll get to the 3D bio stuff at the end, which is of course why we're applying this, but I'll just take you through the algorithm. So constraints. All the time we live with these, a lot of times it's economic. I want a house that has 4 bedrooms and 2 baths. It's out in the suburbs and I want it to cost less than $200,000. Obviously, you can't always match all of your constraints as well as you'd like, but you can do your best. And so really, the process I just took you through was take the set of all houses, remove those that aren't in the suburbs, remove those that don't have 4 bedrooms, etc. Well, let's look at a little more direct application of this process. Some of you may know this game. It's very popular here in the States and in Japan. The goal of it is to get the numbers 1 through 9 on every column, every row, and in every box. The hard bit being that you can only have 1 copy of each number in each of those cases. So I posit to you that this guy right here is a sort of vector in a 9-dimensional space. You can kind of vectorize almost any quantity of data that you like, be they images or stock options or what have you. So for those of you that know the rules of the game, you can see immediately that this 1, 4, and 7 are missing from this middle group here. Now, usually when you play this game, you do some very quick mental calculations and you start rapidly eliminating possibilities and so on, but let's slow that down a bit and just do what your brain is doing in a single step. And I posit that that is trying something out. Let's say, okay, we've got 1, 7, and 4 here. Right? That satisfies this criterion. That was the one we started with. We're missing 1, 7, and 4. It satisfies this one. Okay, so far so good. Oh wait, no, it doesn't. The column has a 4 in it already, so there is some sort of problem. Now, a lot of sort of programming models at this point would say, all right, throw this whole vector away and start over from scratch. Let's choose a new one and see what we get. Well, we know better than that, right? Because we know that, well, these are okay, no problem there. These in principle are okay. So better than that, let's keep the fact that we know that this is probably a vector that's pretty close in our parameter space to where we're going. To just change those little elements of the vector that are not compatible with our constraints. So simple enough. We just swap the 4 and the 7, and while this may not be an overall solution, it certainly satisfies all the constraints that we put forward. Okay, so I had a math professor who once said that a good problem needs to be sort of snuck up upon, and that's the way we're going to approach the math here. So the next layer is kind of, if you think about that in a geometrical sense, is you've got your vector and parameter space. You've got some sort of subset of points in that space. The Sudoku problem, the number of houses in the suburbs, what have you, that restrict your options. You know, we can't choose the whole space. There's just some subset of those options that we can choose. We know that our solution is somewhere in this neighborhood, so we don't want to lose that knowledge. And so what we do is we find the closest point in this set here to our original vector. This is also known as the projection of the vector from one space into another. Written more algebraically, that's shown as here. We have 2 separate constraints. We have 2 types of projections. We apply the first one to a particular vector, and then we can apply the second one. So hopefully, if we do this a lot, if we continue to do this, I mean, it works for any point in this space, but if we for instance, have two spatial constraints and we project it into one space and then the other one, if we do that, well, a lot, eventually, hopefully, we get somewhere that just stops moving. These are known as the fixed points, or the solutions. These are rather similar to eigenvectors in some ways, except that this isn't a linear system. Okay, so let's look at this very quickly geometrically. we're going to be applying this to the modulus constraint, also known as sort of the fact that you have the diffraction amplitudes but not the phases, or maybe you have some subset of phases. And then we've got this so-called supports constraint, which is in a way basically saying that I know that my protein exists inside of a sphere, that it's not infinite in dimension, or maybe I know that it's a crystal and it doesn't go above or below a particular planar spacing. Okay? So that effectively, in our massively dimensional space, is the Hilbert space, we kind of reduce the dimension drastically. And so we start with a random guess, random noise, 0, what have you, and we project it immediately into our support constraint. That is, we take our noise, we enforce the fact that we know it's inside this sphere, then we go into Fourier space, and we enforce the fact that we know the modulus, the diffraction amplitudes. But we've now violated our support constraint, because when we go back into real space, we've got densities outside of our sphere.
Sorry, you lost me. The support constraint is what? Support constraint?
The support constraint is
the fact that the protein is a given entity within a certain radius. Exactly. And what's the modulus constraint?
That's the amplitudes in Fourier space. So when you take exactly. So when you take the diffraction pattern, you know just the amplitudes, but not the phases. And the intersection between those, the line with the surface of the ellipse here, is your true solution. Okay, so we violated the first constraint, so we enforce it again. Now we violated the second, so we enforce that again, and so on and so on and so on. We do this infinitely, and eventually we get here. This is a wonderful algorithm. It works in a lot of cases, so long as your conditions are really good. Yes?
Please allow me now a nasty question.
Yeah.
This is 2D, so the cross between the ellipse and the line has 2 crossover points.
Yes.
If you go to n-dimensional space, you have potentially a very large number of crossover points. So how does the system deal with that?
Well, so generally when we think of functions, when we say sine of x, we get one answer. The projector is not that kind of function. It's a multi-valued function, and we really don't care. We know that there are a certain set of points that satisfy the constraints. It's up to you to make those constraints strong enough and consistent enough to give yourself a result that is either a single or a double. Generally speaking, with modulus constraint, we have 2 possibilities: the vertical and then the inverse tangent form of it, because of the center of symmetry in Fourier space.
But couldn't you now choose a point where you start, where you would actually oscillate between these two in a very, very bad situation?
Yes and no. So you're anticipating here. The solution that I'm showing you here has some nice things known as convexivity and so on, and it guarantees that doesn't happen. The sets that we deal with are non-convex, and so a lot of the math that exists for that theory simply doesn't apply, or it doesn't apply as well. There's a semi-continuous scaling between convex and non-convex spaces. I'm kind of digressing here. So the sort of more non-convex your space becomes, the worse it gets, and you start running into those exact problems. We can talk about that later, though. Okay, so. Where was I? Yeah, so in any case, you apply this a bunch of times. It has a few problems. So the reason, this is just a quick plug for why we're calling this hybrid input-output, that we call it HIO is that there are other ways of going about this that aren't just kind of thunking the system, going back and forth until you finally get your fixed point. It involves these things known as reflectors and so on. It's just a different way to the suburbs, if you will. It's not really a fundamentally different algorithm, although that said it is. Moving on, here's an example. We normally have a 2-dimensional object. As we say in math, without loss of generality, I can talk about a 2D object in the same way that I can talk about a 3D object. It's going to be the same either way. Or you can think of the same concepts. Okay, so if I have my protein and I take the Fourier transform, it's nice and continuous and so on. If I don't, if I go to the microscope and I take a bunch of samples, images and micrographs, I've got all of these projections at every different angle, but you can see that there's a lot of missing information between the planes. That's not so important. What's not pictured, and I will show in a moment, is you're missing loads of information in this vertical direction. Frequently, you're also missing phases in these high tilt directions, but you have amplitudes because diffraction patterns are easier to take. Let's just choose this particular example, and this will probably look familiar to Werner, but we'll go with the interplanar spacing, and then we'll kind of sneak up on the.
So far it doesn't. So.
Yeah. once we, so we're going to just tackle the interplanar spacings, and everything should be seen here as very loose and sort of heuristic, and if you see any errors or so on, don't say, well, hey, I know Emac can do way better than that. Yes, of course it can. I'm just kind of giving you the raw story, as it were, so far. Okay, so the original object looks like so. When you do just a sample...
What is this object related to Werner?
From Frankfurt.
He's Goethe.
Oh.
Yeah, he's the symbol of like. Yeah. In any case, so here he is, well bounded. You can see all of the high resolution details. He's just lost here. Again, single particle programs and Spider and so on. They do weighted back projection and they linearly scale and so on. So this isn't exactly a perfect representation, but it's a good sense that you're losing something here when you do that. Okay, so here's how HIO works. Choose a random space in our parameter space, a point in our parameter space. That's meaning take the constraint that we know, the amplitudes and maybe the phases, keep those, and anything we don't know, we'll just fill it up with something random. Doesn't really matter. Okay, so we back transform into real space. Doesn't really look great, but that's fine. We'll go ahead and mask it out. We know that our Goethe is sitting there comfortably inside of a square somewhere in there. I don't know that it's a square necessarily, so I just draw a big old circle and say it's somewhere in there. We apply that constraint. We go back to Fourier space, but now we've violated the modulus constraint, so we now apply just the information we know. We know just these planes here. We let everything else float free. Come back into real space. Hey, that looks a lot better. We do it again and again and again and again. The reason he doesn't look perfect is because this is actually a sort of ill-posed problem, and I didn't start with enough constraints, and so there are many solutions that would solve this. We'll ignore that for the moment and go a little bit further here. When you compare it to the original, however, you can see automatically that the constraints have been satisfied, and more importantly than that, when you're looking at this data, this image here is consistent with the data that you put into it. The micrographs that you got out of the microscope are still in here in terms of their information. When you do weighted back projection, when you do masking and so on, you're actually in some sense destroying that information and convolving it with a mask and so on. So this has preserved what you said was true. That's one of the most important features of HIO. Okay, so you can just quickly see that there's some resolution increase. The errors aren't really so much important here between the two cases. I'll just quickly go over the missing wedge. Again, interplaning spacing is somewhat of a problem, but you can fix it. This is a huge problem, and you really can't fix it using normal means. But what you can do is, information is sort of like water. You can just sort of take it out of somewhere else, and you can pour it into something else, and as long as you've got enough of it, it'll fill up the volume that you're looking for, if you will. So we can oversample in Z quite easily, just by tilting at a finer increment, and that will inevitably sort of make up for the fact that we're missing this missing cone. If we happen to have phases at low angles, we can actually do even better still. The more information we can pour into this thing, the better the reconstruction will get. So again, we do what we did before. We fill up all of the missing information with random data, go back and forth, eventually fill in the missing cone. The amplitudes are not correct here because of the way that I was doing the reconstruction. You tend to have energy loss when you apply masks and so on. But the phases are correct. And so I'll just quickly show you the sort of generic result here. Again, you can kind of ignore the errors. What you see over here is qualitatively in the missing cone, you tend to have elongation. It's just a typical feature in the sense that you haven't constrained your image in the vertical direction, and so it's free to kind of flow. But what we have done is we didn't know anything about what was out in that missing cone. We just knew vaguely that he was inside of the circle. Again, I used a circular mask, and you can see that his proportions have returned to a pre-missing wedge state. And you can even see some Z resolution that you simply could not see in the direct reconstruction. Again, I'm not trying to imply that yes?
Could you say something about the difference between the right and the left?
Yes.
There's this blurriness, cloudiness in the right one,
yeah,
and there's these sharp lines on the left.
Yeah.
Where does that appear in Fourier space?
That appears in the sense that you see here you've got these extremely sharp lines which represent an entire planar projection. If you just take your projection and you back projection, you just kind of push it or extrude it, as you say, through real space, you get just a sharp line. What you can see here is this sort of bleeding out, right? And so, in some sense, you're actually sharpening the resolution around those lines. The information is, if you will, flowing out from the mask into the neighboring area around these planes.
Yeah, you filled in the missing cone.
To put it, So anyway, filled in the missing cone. High resolution details are there. Proof of principle seems to work. Great thing about it is that we just invented an algorithm where we said, well, I kind of sort of know where my guy is located, and I pretty much know the data here, but I don't know anything about this. That is an incredibly powerful mathematical statement to be able to say, yeah, it's in there somewhere. And to be able to algorithmify that, if you will, is very, it's an amazingly beautiful thing. And, so I'm a bit nervous presenting this because two of the authors of the main paper that I was referencing were at this workshop, one is sitting right here. This has been done in simulation before, so I'm certainly not the first person to do this. But what I've been working on for the last couple of months here is getting it to work on real data, and as well as confirming the simulation results, which of course look quite good. So, a little grain of salt, and we'll move on. Very preliminary results. Please don't fire at me too quickly with what's the resolution of this and see if I don't know. What I'm just trying to show you is that using 2dx/MRC, we managed to get the blue volume of our bacteria rhodopsin data set, and using HIO as post-processing, we managed to get the green volume. All I want you to look at here is the fact that at the same density, at the same isosurface, we've got a bridge where we did not have a bridge before. We've got a more resolved sort of vertical features, and that's really what we're looking for in z-resolutions. Do we have density, no density, density? And in this case, we've actually improved that, and even better than that, you can see a little hole down here has opened up, which was not there before. That's a good start. At least it's a good indication of where we're going. Furthermore, really exciting, maybe even equally important note is a lot of noise reduction. This is kind of out inside the membrane. The blue again representing the MRC reconstruction, the green representing the HIO sort of refined reconstruction. You can see there's a lot of removed noise, and you see a much more well-resolved volume when you look at it outside. Fit the PDB through it. This isn't the most perfect view, but it fits extremely well, and quantitatively I don't have a good answer for you, but we see these loops. When you look at them very carefully at the right isosurface, they just jump right out of the data, and so forth.
So Brian, I
Yeah.
kind of missed this.
Yeah.
What did you put in information?
Oh, right, sorry, I completely skipped that actually. So the data set that the Mitsuoka lab very kindly lent to us for using this was a combination of a diffraction data set that was up to 60 degrees, I want to say, and then there was the real space data set, and we used phases up to about 30.
Three-dimensional phases to 30? Or
Yeah, in three dimensions, exactly. And so it's an extremely powerful constraint to have a few phases. And so the sort of moral of this story is from simulation, and at least tentatively from direct data, if you have data out to, say, 15 or 30 or possibly 15 degrees, you can actually phase your entire diffraction data set using just some very simple constraints. And you almost always know the extent of your protein. Or if you don't, you can kind of get a good guess for it in the sense that you can draw a circle around it crystallographically, and maybe you know how wide the membrane is using other techniques and so on.
Does this work at any resolution?
It does, as long as you have the information to constrain it, absolutely. So the way that John Spence set this up is that he oversamples the z dimension by 3 times, which is the rule of thumb that you mentioned, and then he fills up as much as he can the tilts in between there. And this oversampling in Fourier space is enough to constrain it to the point that you can fill in both missing cone to a degree and certainly face the diffraction.
So I missed even the second time you said it.
Yeah.
This is phases to what?
This is up to about between 15 and 30. Yeah. And then diffraction the rest of the way up to 60. Yeah.
What happens if you don't have diffraction data?
Oh, you can still use this. I mean, if you've got data up to a point, you still need to, basically you need to constrain that missing cone. And there's a very quick rule of thumb that I might write down, but the idea is that if you just measure the amount of real space that is empty versus the real space that is full, and if that matches the amount of information you're missing in Fourier space, then your system is constrained. I can show you that just really quickly on that.
I don't think we have this.
Doesn't matter. Okay, fine. So, any questions on this? Please approach me. I love talking about convex and non-convex set optimization. Quick 3 references here. The Spence paper is invaluable. David Eggert did this middle one, and then this is sort of the definitive bridge between math and physics on this. Oh, I'm so sorry. I just Googled it last night at 1 a.m. So I apologize for any offended parties. In any case, to carry the news theme forward, further updates as events warrant, please check back in a month and maybe you'll have something more quantitative for you. Special thanks and a shout out to John Spence, Dan Seal, and Mike Sarahan, who are actively working there with me, Taro Mitsuoka for providing the data, Starbuck Lab, NSF and NIH for again paying my salary. So thank you.